So in this equation, we're going to be looking at specifically solving sine equations and generating solutions for those. So when we talk about solving trig equations, what it means is that we're actually trying to determine the angles which give that particular sine, cos or tan ratio. And for a trig equation that has an unrestricted domain for that particular angle, what you get is actually an infinite number of solutions for angles that fit that sine value, and those solutions can be generated using patterns that exist in the solutions called general patterns. Let's have a look at generating a general solution for sine. So if we're looking for solutions that involve sine, basically what we do is we rearrange the equation so we've got sine of something is equal to some value. And this will be positive or negative value. Let's just work with just the positive one just for the minute. And so from our work with finding values of sine and cos for angles in the unit circle, we know that for a particular point on the unit circle, so this point here on the unit circle, we know from previous videos, if you haven't watched it, but we know that the value of the x coordinate is our cos value for that particular angle, and that the value of the y coordinate is in fact our sine value for that particular angle. And so if we're trying to solve something for sine of something is equal to b, what we're looking for is what angle in here has a y coordinate of b. Okay, so I'll say that again. What angle goes in here that gives us a y coordinate of b? So let's have a look at our points around the unit circle. I've got one here, this first point marked here, that has a y coordinate of b. So sine of theta is in fact b. So we'll write that as one solution. So we know that sine of theta is b, so therefore theta is a solution. But we also have around the circle this second angle here, which is theta back from pi. So what we're actually measuring is this angle this way, which is the angle of pi minus theta. And so that's another one of our solutions. We know that sine of pi minus theta is equal to b, and so therefore pi minus theta is a solution. So both of these angles have a sine value here that is b, and so they're both solutions, but they're not the only one. We know that we can continue around to 2 pi and go again, which will give us 2 pi plus theta. So that's a solution as well. You can continue on your journey from 2 pi plus theta around to this point again, which will be 3 pi minus theta, which is in fact 2 pi extra added on to pi minus theta. Can you start to see a pattern? We have theta as a solution and theta plus 2 pi as a solution. The next revolution around, a complete cycle added on to pi. And pi minus theta, if we go around the circle again, we're just adding another 2 pi onto this solution. So we have a pattern. Once we have our two initial solutions, which are theta and pi minus theta, then we can generate an infinite number of other solutions by adding 2 pi onto each of our answers from there. So that might look something like this. So the yellow column here has our solutions for theta at this point up here, and each time we rotate we're adding 2 pi to get to this value again. So we've got theta, theta plus 2 pi, theta plus 4 pi, theta plus 6 pi. So what we're generating here are even numbered multiples of pi plus theta. This second column shows you all of the solutions that I've generated from my second solution point up over here, which is now off the screen. So each time from here to here, we're adding 2 pi. You can see that it's going up by 2 pi. So another way to think about these solutions and adding 2 pi to them is to think about it in terms of the graph of the function. And so I'm going to draw a graph over here and show you how the points are linked together. So here on this graph, if this is our b value that we're trying to find, our y coordinate for the point, then we're looking for this first point here to be our first intersection point, theta, and then from there we move 2 pi when we go around a circle, and we end up at the same point on the graph 1 period later. And if we added another 2 pi, we'll end up on the same position of the graph on the next cycle to the right hand side. Or we can come back this way and go minus 2 pi, which will bring us to this point here on the graph, which is also 2 pi distance from that point. Our blue values are pi minus theta, which is this value here. Now on the graph that I've got here, this axis is in radians. You can see that this is 3.14, so this is in fact pi radians. And so from our first point, we're going to add 2 pi to our value to get to here, to this second point. And if we take 2 pi off of our original point, we'll come back this way and we'll end up at this point here. And so what we're actually solving for, our b value that we're solving for, is this line here. This is our b value. And we're looking for where does the sine curve touch that line for b. That's what are the solutions that we're generating. And so now we're going to have a look and see if from the values that we have from this table over here, can we come up with a general pattern that we can use to generate all of these solutions. Now to come up with a way of writing a pattern for this, what I'm going to do is I'm going to write them in order of increasing number of pi's. So if you follow me backwards here, we've got 7 pi, 6 pi, 5 pi, 4, 3 pi, 2 pi. This is 1 pi and this is 0 pi. And I'm going to write them in order because we're going to get a general solution pattern from this. So now you can clearly see that we have increasing values of pi going up 0, 1, 2, 3, 4. And every single one of them has either plus theta, minus theta, plus theta, minus theta. And you can see that the positive and negative in the middle here is switching from one to the next, to the next, to the next. So I'm going to show you a little trick on how we can generate this particular pattern using these coefficients of pi at the front to come up with a general solution. So this might be a little bit weird, but what I'm going to use is a switching factor of minus 1 raised to the power of whatever my coefficient of pi is. So for this equation that I've written here, minus 1 to the power of 0, anything raised to the power of 0 is 1. So what I've essentially got here is plus 1 theta or plus theta, which is what I've got here. Now I'm going to do the same with 1. So 1 times pi, the minus 1 is now raised to the power of 1, which gives us a negative 1 as a coefficient for theta, which provides us with this minus sign here. See where this is leading? Let's have a look at the next one with a 2 here and a 2 here. So we have 2 pi, which is what we need. We need a positive value here, and minus 1 squared Minus 1 times minus 1 makes positive 1, plus positive 1 is still just a positive, and our theta value. You can see the pattern that we're starting to get here. Let's just double check it with our next two answers. 3 pi, that's right. Minus 1 to the power of 3 gives us a negative answer, plus a negative gives us the minus we're after. For the last one, we've got 4 pi, and minus 1 to the power of 4 gives us a positive 1, plus positive 1 gives us the positive that we've got here. So we've definitely got a pattern here. And so what I'm going to do is I'm going to replace this coefficient at the front with a counter that I'm going to use the letter n as our counter. And so our general solution is going to have an n for our counter position here, and also for our power of minus 1. So here is our general solution pattern. Our counter times pi plus minus 1 raised to the power of our counter times by theta. Now there's two other things that we need to define here. This n is our counter and it's increasing by whole numbers. So we need to state that n is an element of our integers so that we can put only whole numbers in there. And the other thing that we need to define here is that this theta is our original solution in the first quadrant. For sine of something is equal to b. Now, if you're writing a solution, a general solution pattern in the exam, you need to make sure that you include your specification for z and that you include what your original solution was that fits there. What's the original angle? Might be pi on 3, might be pi on 4, it might be pi on 6, but it definitely needs to go there. And so we can use a series of z values for n. We can use a series of both positive and negative whole numbers to generate a list of solutions. And I'll show you that in a table below. So I'm going to show you for n is minus 2 that you substitute in minus 2 pi plus minus 1 to the minus 2 and theta, and where that will be in the unit circle. So some simplifying here. To the power of minus 2 means 1 over whatever it is squared. So this still becomes a positive, and we're left with minus 2 pi plus theta. Now on the unit circle, if we start at 0 and go minus 2 pi, that brings us around to here. If we then add theta onto that, that brings us back to here, puts it in our first quadrant and gives us the solution that we want. For minus 1, we get a formula that says minus 1 pi plus minus 1 to the power of minus 1. So if we tidy that up, we get minus pi. This becomes 1 over minus 1 to the 1, which gives us our negative. So minus pi minus theta on the unit circle, minus pi, and then minus another theta brings us around to this quadrant here. And this is our second point that we found that had b as its coefficient for y. Let's look at 0. So 0 pi plus minus 1 to the power of 0, that gives us a 0. Minus 1 to the power of 0 is 1 theta, so it's just theta, so we're back to this angle here. And you can see if I keep increasing my counter, I'll generate the next sets of solutions all the way along. An alternative method of writing a general solution for sine is based around using combinations of these two pairs of solutions that are generated here. And so what you do is write both patterns in terms of this pattern here. So let's look at this. This is an even number plus theta, and its corresponding pair is one more than that even number times by pi. So 2n plus 1 pi minus theta. And that generates each pair of numbers. So for this pair here, n is equal to 1, because 2 times 1 gives you 2, and 2 times 1 plus 1 gives you 3. For this next pair here, n is equal to 2. For this next pair here, n is equal to 3. And so this is an alternative way, and this is actually the way that they've got it written mostly in the book. Again, you need to make sure that your n is an element of z, and we're going to actually write, instead of that angle theta, we're going to write it as the solution to inverse sine of b, which is of course theta. So our solution is a very big one, this solution or this solution. And remember, you need to write that n is an element of z. To find solutions for sine of something is equal to negative b, it means that our y-coordinate needs to be negative b. So we're looking at the angles in the lower half of the unit circle. So instead of working with pi as one of our angles, the first angle we're going to work with is in fact minus, not pi, theta, minus theta. And so we can still use our general solution pattern from before. It's just that this time, instead of substituting in pi, we'll use the fourth quadrant version of it, which is minus theta. And that will generate all of our solutions for us, the same as the positive version of theta generated our other solutions for positive values. So I've calculated two of the answers for n equals 1 and n equals 2. When n equals 1, one of the solutions is pi plus theta. So we go around pi plus theta. So that's giving us this solution here. When n is equal to 2, and I'm using this minus theta, you get 2 pi. This gives us a positive value. So we've got 2 pi plus negative theta, which is 2 pi minus theta. So that gives us 2 pi around to there plus theta. That's giving us this angle here. So you can see by simply substituting in the fourth quadrant value, or negative theta, for a negative solution, because the sine values are in the negative half, using this first answer and the general solution, we generate the correct answers. So in summary, that you've got two general solutions for sine of x is equal to b. You can use inverse sine function to generate one solution, and from there you can use these general solution patterns to generate multiple versions of that answer. So you have the first one that includes the skip counter, and then this second one that includes the two versions of each answer. Just need to remember, if you are working with b as a negative number, that the answer that you get, the angle that you get, the one solution that you'll get will be a negative angle. I'll do general solutions for cosine and tangent functions in a follow-up video, and if you look at the top left-hand corner, if you click on that, that'll take you to that video.